So good morning, all of you. Today we would be learn the topic that is constant current bias with Zener diode. So in the last lecture, we have seen that the constant current with bias by using the voltage divider network as well as the diode for the temperature control. Now we have to be use uh, Zener diode as one of the alternative for performing the constant current. So if you have to be see in the diagram, it is very much clear. We have connected a Zener diode in the base of the transistor Q3, and you can see here, instead of diode and the resistor R1, we have replaced this with the Zener diode. And as we know that Zener diode would be operate in the reverse bias condition. So here you would be indicate this is the positive sign and here is the negative sign. So at the cathode end, we have shown the positive, and the anode, we have the negative here because it would be work in the reverse bias condition. Now, Zener diode is available over a wide range of voltages and can have matching temperature coefficient. So in this circuitry, all of you please draw this diagram. You can see that the current flowing through the R2, that is one end of the R2 is connected to the ground actually. So it is I2. The current entering into the base of the Q3, that is IV3. The current flown into the collector terminal, that is IC3, and the current coming out from the emitter one, that is the IE, or you can say IE3 as well. And the resistor is the RE, that is connected to the anode of the Zener, as well as the RE would be connected to the negative power supply, that is minus VE. Okay. So this I2 would be divided into two parts, IV3 and I3, that is flowing across the Zener. Now we have to be see the equations of the current that is flowing through the uh, transistor Q3 and the Zener diode, as well as we have to be calculate the voltage also. So we have to see that in that circuitry, the first one is the voltage at the base terminal. So what is the voltage at the base terminal? You can refer it as a VB3. That would be nothing but the voltage across the Zener diode, okay, and this negative power supply minus VE. So what will be there? You can see here VB3 minus VZ minus VEE is equal to 0. According to KVL, we have to apply on this network. So it would be VB3 is equal to VZ here actually VB3 minus VZ plus VEE is equal to 0. That would be further could be written as VB3 is equal to VZ minus VEE. That is mentioned here. So VB3 is equal to what? VZ minus VEE. So in this way, we can also calculate VE3, the voltage at the emitter terminal of Q3. That is nothing but VB3 minus VBE3. So it is very much clear from the circuit diagram. What is the VE3? V3 is the voltage at this terminal, emitter terminal of the Q3. So it would be nothing but total voltage VB3 minus VBE3. That would be equivalent to the VE3. So we have already defined the equation for the VB3. That would be substitute in this equation. That would be equal to VZ minus VEE minus VBE3. So in this way, we can calculate the emitter voltage of the transistor Q3. If you once calculate the emitter voltage, you can easily find out the emitter current IE3, that is the voltage on the emitter terminal divided by the resistance RE. So here it is VE3 minus VEE upon RE as per the circuitry. So VE3 plus VEE upon RE, okay, and we have to be substitute the value of VE3 here. So you would be get VZ minus VEE minus VVE3 plus VEE upon RE. So this VEE and this VE would be cancelled out, and finally IE3 would be VZ minus VBE3 upon RE. This is the current that would be flowing through this emitter terminal, and it would be independent of the temperature, because the diode Zener voltage would be balance the change in the voltage across the base to emitter terminal of the transistor Q3 due to the temperature change. Okay, in this way we can also provide a constant current into the emitter terminal of the Q3. And one more thing you have to be remember, when you have to be select the value of the R2, it should be keep in mind that the value of I2 should be greater than 1.2 times the minimum Zener current IZ. So here IZ is what? It is the minimum current required to cause the Zener diode to conduct in the reverse bias region. Okay, so R2 would be what? As per the circuit diagram, we can easily calculate the value. Sorry for interruption. So R2 would be what? R2 is, from the circuit diagram it is very much clear. R2 is what? R2 is the resistance that is flowing in this particular network. So it would be nothing but the voltage across this terminal and the divided by the I2. That is mentioned here. So R2 is equal to VEE minus VZ upon I2. As per the circuit diagram, it is very much clear. So what is the voltage across R2? That is VEE minus VZ. This is the term voltage here upon I2, that is nothing but the value of R2. Okay. So in this way, you can also find out the resistance and as well as the I2. Okay. And this minimum condition should be satisfied. Then and then only we can counter the change of the temperature. Okay. So this is the one of the another method that is used for constant current biasing for the differential amplifier. Now the third method we have to be go for this, actually fourth method for a constant current biasing is that is current mirror circuit. You can also use a current mirror circuitry along with the transistor Q3. Okay, so in this case, if you have to be see this circuit in which the output current is forced to equal the input current is said as a current mirror circuit. So thus in the current mirror circuit, output current is a mirror image of the input current. And if you have to be seen this diagram, you can also note it down, the diagram. We have replaced the Zener diode through a current mirror circuitry, that is we have using another transistor Q4 and shorted the base terminal of Q4 with the base of the Q3 in such a way that whatever the current that is into this particular transistor Q4, that would be same current would be flow across the transistor Q3. So I2 would be here equivalent to the collector current of the Q3. Okay. So how this would be happen, we have to be see. Also you can see in the circuitry as per the division of current in this particular node, that is according to KCL, it would be divided two parts, IC4 and IE. Then at this terminal again it is sorted actually. So you can say that IB3 is flowing into the base and IB4 is into the base of the Q4. Actually both are equal. So I is divided into two equal parts, IB3 and IB4, because we have considered that both the transistors are matched also. So if it is equal, so obviously IC across collector current across these two transistors would be also equal. So we have to be see this all analysis with the help of the mathematical equation. I hope all of you have taken the screenshot of this diagram or drawn this diagram. This very simple one. Now see the mathematical analysis of this, how it would be happening. And we have to see that once the current I2 is set up, the current IC3 is also automatically established, that we have already discussed. And current mirror is a special case of constant current bias. And current mirror bias requires a constant current bias. Therefore, can be used to set up the currents in the differential amplifier stages. So current mirror bias require very few components to establish a constant current. Only we have to be required answer Q3 and Q4, that is identical in nature, so that the current flowing across these two transistors would be same, as well as the voltage across the terminals would be also same. And this is very important, consider that both transistors should be identical for the satisfactory operation. So here you can see that according to circuit diagram, if you remember this circuit diagram, I will again showing you the circuit diagram, that both the transistors Q3 and Q4 are exactly matched. So all the terminal voltage and current would be considered as the same. Okay. So here, if you have to be see, VBE3 is equal to the VBE4 base 2 emitter voltage of transistor Q3 and Q4 are equal, as well as both the base terminals are shorted, so IB3 and IB4 are equal. If IB3 and IB4 are equal, so IC3 and IC4 are also equal, because we know the relationship between the base current and collector current. So if base current is same and both the transistor match, so yeah, this beta is also same, so IC is also same. Now summing the currents at the voltage node, that is VB3, you have to be remember the diagram. So here I2 is equal to the I plus IC4. So we are referring the same picture. So in this case, I2 is equal to IC4 plus I. IC4 plus I is what? Again dividing into two equal part, IB3 and IB4. So it is, you can further write it as IC4 plus IB3 plus IB4. I divided into equal part. And as we know that IB3 and IB4 are equal, so you can write it as twice of IB4, that is equivalent to the IB IC3 plus twice of IB3, both are equal. Now you can further write it as I2 is equal to IC3 plus IB3 means what? According to this equation, it is IC3 upon beta DC. Okay. So it is become equal to, we have to take the IC3 common. So it would be become I2 is equal to IC3 into 1 plus 2 upon beta. Okay. And generally beta is very large. So what happens? 2 upon beta would be considered as a small quantity. Generally beta, the value of the beta is 50, 100, 500 like this. So it is a very large quantity, is current gain parameter. So 1 upon beta is a very small quantity. Similarly, 2 upon beta is also very small. So we can neglect the effect of this term on this equation. So your equation would be now approximated as I2 is equivalent to the IC3. So whatever the current entering into the transistor Q4, this is equivalent to the current flowing on the collector terminal of the transistor Q3. And what is the value of I2? On which factor the I2 depends? You can see here, I2 is equal to VEE minus VBE3 upon R2. You can refer this diagram. So what is the I2? If you have to be see that, as the I2 and IC3 is same, so what is I2? You have to be follow this route for the KVL. So it would be become VEE minus VBE4 upon R2. Okay, you can apply here from like this 0. This is the ground. This is 0 minus come to this end because base and collector are shorted. So same VBE4 is same as a VCE4. Actually, both are shorted here. So it is minus VBE4 minus VEE is equal to upon R2. That is your I2. Okay. So you can say VEE minus VBE4 upon R2. That is mentioned on the equation also. Okay. And VBE4 is nothing but VBE3. Okay. So you can write like this. So in this way, we have seen all the possible configurations for providing the constant current biasing into the differential amplifier. Okay. Now we have to move to the next stage, that is the level shifting stage are there. So the next point is topic is level translator. So we are moving one by one block of the op-amp, starting from the input stage, that is one differential amplifier, then the intermediate stage, another differential amplifier. Now we have entered third stage, that is the level translator. So if you have to talk about the level translator, because of direct coupling, the DC level at the emitter rises from stage to stage. We are moving from one stage to second stage. We are using the same differential amplifier configurations, and because of the direct coupling, what happens? The DC level at the emitter terminal would be rises from one stage to the second stage to third stage, and this would be increase the DC level. That tends to shift the operating point of the succeeding stages. Means from input to the intermediate, and then we have come to the level translator stage. So when we have to be moving from one stage to second stage and second to third, this DC level has been be shift to the operating point of this succeeding stages, and therefore it limits the output voltage swing, because when the DC level would be shift from the reference zero level to some positive value or some negative value, whatever, so there would be some restrictions for the voltage swing at the output terminal of the op-amp. And now if you have to be applied the same signal as you have applied for the zero reference level, it would be now clipping. The problem of the clipping is there, and it could be actually say the distortion of the output signal. So to avoid the distortion and to provide the maximum voltage swing at the output terminal, we have to use the level translator circuit. So what is our aim? To shift the output DC level to 0, and for this purpose we are using level translator. So now see, this is the most basic structure of the level translator, that is nothing but an emitter follower circuit. You can see here, it is an emitter follower circuit with voltage divider network. It is the simplest form of the level translator. So at the emitter terminal, we have used a voltage divider network by connecting two resistors R1 and R2, and the another end we have the negative power supply, and we have to be calculate the output in middle of the or in between of R1 and R2. Whatever the voltage across this R2, that is nothing but the output of this level translator. So there's a DC voltage at the base of the transistor produces a zero output, and how it would be decided? It is a zero output. It would be decided by the value of the R1 and R2. Okay, so it is very much clear that R2 upon R1 plus R2 VEE, you can say it is a negative. That would be nothing but the output voltage. Okay, according to voltage division network. If you have to do the amplitude, so this will be the positive sign is there. Okay, amplitude part. So in this way, the value of R2 and R1 would be decided. The value of the output voltage would be 0 not. Okay, now instead of this voltage divider emitter follower, you can also use the diode current bias or current mirror bias that already we have seen for the better results. In this case, which is a common collector amplifier, what we have shown in the diagram, emitter follower, the voltage it would be shift up to the 0.7 volt. Means if you have already the DC level has shifted to the up to the 0.7 volt, it would be bring down to the 0. If this shift is not sufficient, so output may be taken at the junction of the two resistors in the emitter leg. These are the some also another alternative configurations available for the level translator, where we have connected the emitter follower along with diode network as well as the current mirror biasing network. So either you can use a voltage division network and for the emitter follower, or you can use in this way two diodes are connected in series, or you can use a current mirror circuit. All are giving you a good result. Okay, so you can take the screenshot of these diagrams as well. Now this is up to the level translator stage. This is the complete circuit diagram of the op-amp, where we can see easily there is a input stage that we have already discussed, intermediate state we have discussed in very detail, as well as the level translator today we have discussed, and final stage output stage, that is a push-pull amplifier. Okay, so in this way these are the 4 stages or building blocks of the op-amp. Now we have to be moved to the next topic, that is parameters of the op-amp. The first parameter we are going to consider here is input offset voltage. So this is the diagram that I have shown you. Please draw this diagram, it is very important. And we have to see what is the actual input offset voltage, the definition of this. Input offset voltage is defined as the voltage as the that must be applied between the two input terminals of the op-amp to null or zero the output. Okay, so amount of voltage between these two terminals would be applied, that would make your output voltage 0. So what happens actually, if suppose you have connected both the inverting and non-inverting terminals to the ground, means we have applied a 0 volt as input, it is expected in ideal case your output voltage should be also 0. But due to the mismatching of the transistors that is responsible for the construction of op-amp, what happens, even you have applied the 0 volt at the input, you are getting some amount of finite voltage at the output, and that is nothing but a offset voltage. So our aim is to make this offset voltage 0. Then for this purpose, we have to be apply the voltage in between this inverting and non-inverting terminal, and the amount of voltage that would be applied to these two terminals, that would be make your output voltage 0. That is called the input offset voltage, and it is written as VIO. In some books they have used the VOS also as a offset voltage. You can use either of the notations. That is equal to input voltage at the non-inverting terminal minus input voltage at the inverting terminal. Okay, this is called as the input offset voltage. It is very important parameter. Now come to the second parameter. I hope all of you have drawn this diagram. Please draw this diagram. I will give you 30 seconds for this. Okay. Now you have, I think all of you have drawn the diagram. So VIO is what? It is the difference of VDC1 and VDC2. And remember that this input offset voltage could be positive, could be negative. Now we have to take a reference IC op amp, that is 741, and see what is the value of this parameter. So for 741 op amp, the maximum value of the input offset voltage is 6 millivolt. This is a very important value. We have to remember this. It means a voltage that is plus minus 6 millivolt is required to one of the input terminal to reduce the output offset voltage to 0. And smaller the input offset voltage, better the differential amplifier, because it means that the transistors that is used to construct the differential amplifier are closely matched. How much the smaller is the value of the input offset voltage, it is more better for the op amp operation. Now we have to move to the second parameter, that is input offset current. Input offset current. So what is the input offset current? Input offset current is IO is the difference between the current into inverting and non-inverting terminals of the balanced amplifier. It is a difference of the applied current into the inverting and non-inverting terminals of the balanced amplifier. So IO, that is input offset current, could be written as the difference between two base currents IB1 and minus IB2, or you can take the amplitude only, magnitude part. We have not shown the sign. You can take this amplitude part only. So you can consider IB1 is applied to the non-inverting terminal and IB2 is applied to the inverting terminal of the op amp. And the value of the input offset current for 741 is 200 nano ampere maximum. Okay. As the matching between two input terminals is improved, the difference between IB1 and IB2 becomes smaller. How much the transistor would be more matched? Your input offset current would be more less. Means your input offset current would be decreases. For example, if you are talking about the precision op amp 741C, your input offset current is 6 nanoampere only. So what is the precision op amp we would be see later on in the further discussion. all types of the op-amp or the configuration we would be going to learn in the unit number 5. Now, the third parameter is input bias current. So input bias current, IB, it is the average of the current entering to the input terminals of the balanced amplifier. That is, IB is equal to IB1 plus IB2 upon 2. So you can understood with the help of this diagram also what is the input bias current. You can draw this diagram, whatever I am drawing here. So it is your IB1, this is your IB2 at the inverting terminal. The average of these two currents would be considered as the input bias current. And the difference is their input offset current. So for 741 IC, the maximum value of the input bias current is 700 nanoampere. And for the precision 741 op-amp, it is very small, that is plus minus 7 nanoampere. So you can see that in the precision op-amp, this is very small. Okay. I hope all of you have drawn this diagram as well as noted down the equation for input bias current. Now we have to see the next parameter. That the fourth one is differential input resistance, RI. So what is the RI? RI is the equivalent resistance that can be measured at either the inverting or non-inverting input terminal with the other terminal grounded. Okay, so it is just an equivalent resistance that can be measured at either of the inverting or non-inverting terminal by considering the other terminal is grounded. So for 741 op-amp, it is input resistance is nearly or relatively as high as 2 mega ohm. But for some op-amp also it would be goes up to the some giga ohms, thousands of giga ohms. It is very high value. So op-amp having the very high input impedance. That's why there is no current would be allowed to enter into this op-amp. Now we have to move to the fifth one parameter, that is CMRR, that we have already familiar with this. We have already discussed this. So CMRR is defined as ratio of differential voltage gain AD to the common mode voltage gain ACM, and it could be referred as CMRR is AD upon ACM. For 741 IC, common mode rejection ratio is 90 dB typically. The higher the value of CMRR, the better is the matching between the two input terminals of the op-amp. And would also say that it is a smaller the output common mode voltage. So it is required that the value of CMRR should be very high. For ideal op-amp, it is nearly infinity. The sixth parameter is that supply voltage rejection ratio, or it is also said as power supply rejection ratio. Now everyone, you can start to enter your attendance on the chat box. So the definition of this supply voltage rejection ratio is SVRR or PSRR is, it is a ratio of change in input offset voltage to the corresponding change in the power supply voltage. So it is a ratio of change in input offset voltage with respect to the change in the supply voltage. And this is expressed as millivolt upon per volt, or maybe in decibels. So you can say SVRR is defined as delta VIO upon delta V, where delta V is the change in the input supply voltage and delta VI naught is the corresponding change in the offset voltage. So this is the sixth parameter of the op amp that we have to be remember, supply voltage reaction ratio. For 741 IC, SVRR is nearly 150 microvolt per volt. So means there it is a per volt change in the supply voltage, there is a 150 microvolt change in the input offset voltage of the op amp 741. Seventh parameter is output swing. So output voltage swing. The AC output compliance PP, that is peak to peak, is the maximum unclipped peak to peak output voltage that an op amp can produce. So since the quiescent output is ideally zero, so the AC output voltage can swing positive or negative. This also indicates the value of positive and negative saturation voltages of op amp. The output voltage never exceeds this limits for a given supply voltage of plus VCC to minus VE. Generally for 741 IC, it is plus minus 13 volt. So that we would be see later on how the output voltage swing would be represented. So today I stop here because the time is not left. For the next lecture, we would be see rest of the parameters of the op amp. Still, we have discussed the DC parameter. We have to also discuss the AC parameters, and also we have to be compare the ideal op amp with the practical op amp. Okay, thank you all of you for attending the lecture today.